This is AS2 Physics 2 January 07, question 4. Part A, figure 4.1 shows a sinusoidal wave disturbance W1 and a blank axis for two other waves W2 and W3. So I'll just show you that for a minute. The wave W1 arrives at a certain point simultaneously with a second wave disturbance W2, so that complete constructive interference occurs at the point. On figure 4.1, draw the waveform of W2. So if we have a wee look here, you can see there's W1. If you want that to completely constructively interfere, you want a wave of exactly the same size, amplitude and so on. And so we're just going to mark in a couple of points here to make sure that I'm drawing them in the right place. And that's up there. Okay, so it's completely in phase. It then says wave W1 now arrives at another point simultaneously with wave 3, so that complete destructive interference occurs at this new point. Draw the waveform of W3. Now that must be completely in antiphase, and since we'll just compare it to W2 there, since it's exactly the same as W1, and so it's going to be the opposite way round, with your troughs corresponding to crests on the wave above, and they have to be exactly the same height. It's just a wee bit, okay. Alright, then state the wave difference between W1 and W3. So there's W1, same as W2, and there's W3, and you can see they're completely out of phase, which is 180 degrees. So the answer there is 180 degrees. Part B, figure 4.2 shows two waves S1 and S2. On the blank axis 4.2, sketch the resultant wave S3 when the superposition of the waves S1 and S2 occurs. Now, when I looked at this originally, I thought, how could you do that? And it's just too difficult to think about this precisely. But what happens there is that this superimposes on top of this wave here. The shape of the wave isn't going to change at all, but the actual waveform itself will be just jaggy. And so it's got exactly the same wavelength and frequency and so on as it always had, and it's not going to go that much above where it is, a wee bit above it. So that's where originally is at the minute. Down there. So I'm just going to draw this first of all, and then I'm going to draw a green wave on top just to show the new waveform. And you could do this yourself. You could draw it in pencil and then draw a wave on top of it. And so this has become all jaggy. And the green waveform there is the answer, the jaggy one. The frequency of S1 is 100 Hz, that's this top one, and the frequency of S2 is 5 Hz. Find the period of the superposed wave S3. Now S3 is just going to have exactly the same time period as S2, because obviously it's just this wave with this one on top of it, and this one hasn't made any difference to its time period. And so we're just going to do a calculation. We know that we're going to use the S2 value, and therefore the time period is equal to 1 over the frequency, which is 1 over 5, which gives you 0.2. In Young's double slits experiment, the separation of the slits is 0.6 millimeters. The slits are 2.45 meters from a screen on which an interference pattern is formed. The spacing between a maximum and the neighbouring minimum in the interference pattern is 1.3 millimeters. Calculate the wavelength of the monochromatic light used to obtain the interference pattern. So our equation is lambda is equal to AY over D. And you can see there the spacing between the maximum and the neighbouring minimum is 1.3 millimeters, but we need the spacing between the two, sorry, I should say that again, if those are your fringes there, those are dark fringes and there's a light fringe, they're telling you the spacing between a maximum and the neighbouring minimum is 1.3, but you need the total distance there, so that's 2.6 millimetres. Okay, so the numbers you're putting in there are your 0.6 millimetres, which is multiplied by 10 to the minus 3, your 2.6 millimetres, which is by 10 to the minus 3 as well, and then your 2.45 metres. And when you do that calculation, that comes out as 6.37 by 10 to the minus 7. And you should always, that calculation there, you should always check. You know that the wavelength of light is between 400 and 700 nanometres, which is 4 by 10 to the minus 7 up to 7 by 10 to the minus 7. So if that fits in there, then you know you've got the right answer.